Okay, so all right, so the session is being recorded. Session's being recorded now. Let me give you a few moments to copy down this example, and then I'm going to talk a little bit about linear algebra. But let me give you a moment just to copy the example down. Michael, do you have a question? Okay, all right, and Joel, or you're good? All right, and can everybody can good? I'm assuming everybody can hear me because you all gave thumbs up. So, all right, so what we do in linear algebra is we're interested in solving systems of equations. Okay, systems of equations. So you had, for instance, maybe in algebra or pre-calculus, how many recall solving a system of two equations? Like I'll give an example here. Like how many remember solving a system, maybe something like, x plus 2y equals 6 and 3x minus y equals 4. How many recall, like in Algebra 2, solving a system of equations like that? Sure, Matthew knows what I'm talking about, and you learned, well, there are two ways to solve that system. You could use the substitution approach, or you could use the addition subtraction approach. Thank you, Michael. Yes, and Tizab, and so you've solved systems of equations before, but traditionally it would be, maybe where well, each of these equations represents a line, and so if you have got in the solution would be where the two lines intersect. And you might have even had a problem where you would solve a system where you had three equations with three unknown variables like x, y, and z. How many maybe did a problem like that in their past, where you'd have three equations and three unknowns? Okay, Michael's seen that. Max? Yeah, and so, and in that case, with three equations and three unknowns, yep, Divahar has seen that too. So a lot of you, Vivian, Matthew, okay, so so three equations with, like, when you have an equation, a linear equation with three unknown variables, that represents a plane. So so you've dealt with systems of equations where you're trying to find solutions. Do the two lines intersect at a point? Do the three planes intersect at a point? And that's fine. But what if you had, what if you had 50 equations with 50 unknown variables? Okay, are you going to do it? Are you going to be able to solve that system, an equation? Or maybe that's too big. Let's say you had a system with 10 equations and 10 unknown variables. 10 equations, 10 variables. Are you going to solve that system using substitution? Hey, you could probably do it, but you're not going to use substitution. And Matthew says it would be a lot of work. Yeah, it might take you a month to do that. It would be, who knows, maybe less. But the point is, in applications, we have systems of linear equations where we have very, very large systems of linear equations with a lot of variables. And we need an approach to solve those systems that's very, very structured, and also something that could be programmed in a computer if need be. So we come up with something called elementary row operations. Now in this system here, in this system of equations, of course we have three equations with three variables. So this is really, these three equations represent three planes. But we're not going to use x, y, and z anymore. We're going to use x1, x2, and x3. Because, we could have x1, x2, x3, x4, x5, x6, and so forth. We could have a lot of variables. So, and the American alphabet, the English alphabet only has 26 letters in it. So, we need to have something a little more general. What we want to do is we want to solve the following system using elementary row operations, and that's assuming the system has a solution. But this system will have a solution. So what we want to do is we don't want to carry the variables around. Okay, we want to just carry the numbers around, because it's the numbers, the coefficients of x1, x2, and x3 and the numbers on the right that determine how the that ultimately determines the solution, right? That ultimately determines the solution. So what we're going to do is we're going to write this system as a matrix. We're going to write the system as a matrix. And of course I'm going to go to the solution, but let me just see if maybe well, that isn't working the way I want to. Let me just go back here. Hold on. Okay. So the first equation is negative 4x1 plus 5x2 plus 9x3 equals negative 1. I can write that equation just by putting the coefficients here, negative 4, 5, 9, and then the number on the right last. And sometimes what you'll see, I don't know if maybe you've seen this in past math classes, but they'll draw a dashed vertical line to separate out the coefficients of x1, x2, x3, and the constant that comes after the equal sign. I mean, you have to have something that comes after the equal sign, right? Or you wouldn't have an equation. Right? So you see, you can write this system of equations and not lose any information by writing it as an augmented matrix. How many maybe have seen this in a class before? Maybe a little bit. Self-study, Michael's seen it, Justinas and Vivian's seen it. Okay, good. Okay, great. And many of you have. Wonderful. Well, you know, so basically the row up, we can work with these system of equations and do what we need to do to break the system down so that we can solve it. But we don't have to carry around the variables. We know, for instance, -4 and 0 and 1 here, you know, in the first column there, we know that those are the coefficients of x1. 5, 2, and -2 are the coefficients of x2. 9, -8, and 1 are the coefficients of x3. Okay, and then you have the constants on the right. So, so what we're going to be doing in this class is taking systems of equations and writing them in terms of augmented matrices. Are there any questions so far? Okay, so let's go ahead and get to the solution. We're going to use what's called elementary row operations. And I'm going to show you some elementary row operations when we go through the solution. So I know the book, of course, and you should, you know, the ebook will have different sort of definitions and things, and that's good. But I tend to like to reinforce definitions by doing examples. Let's go ahead here and work through the problem and see, you know, see how to work this problem. So first of all, what I do is I write down the augmented matrix. And the thing is, I know, like in some of our more, like certainly I've seen this in some of our more basic level courses in the math department, where they talk about these, you know, row operations and matrices. They'll draw that dashed vertical line. They'll draw a dashed vertical line so that you understand that it's an augmented matrix. But in our level, we don't need that dashed line. If you see if they tell you, hey, this matrix represents, this is an augmented matrix, then if it's an augmented matrix, you know that the rows, each row is an equation of a linear system of equations. And what we want to do is we want to try to simplify this system. So one thing I'm going to do is I'm going to do what's called a row switch. And I've denoted that here on the right. Now, this is sort of a, you know, I have the first part of this example typed. Normally my work, you know, I work it out and don't type it, but I just have this typed. Okay, so what did I do here? What did I do here? I took row 1 and row 3 and switched the rows. Are there any, and I denote this by row 1, row 3 with the double arrow notation there. That means I swap the rows. I switch the rows with each other. Row 1 and row 3. Are there any questions so far? Oh, yes. What this means here, this little tilde symbol means that this system here of equations is equivalent to this system of equations. And that's the notation you want to use. So like on exams, okay, notation is important. I do count notation as part of the grade. So you want to use proper notation. And believe me, it will help you immensely. Oh my goodness, it will. Okay, so why did I switch row 1 with row 3? Why did I choose to do that? The reason is that by doing that, I have a 1 in the top left-hand corner of the matrix. 1 is a number that you'll find you love. You will love 1s. And what we want to do is we want to put this, I want to say this the right way. I want to basically try to get as many zeros in the matrix as possible, because in other words, I want to rewrite the system of equations so that the equations are easier. Well, what's easier than 0, right? So what my plan is I'm looking at the first column here, and I see that I have a 0 here in that spot, but I have a -4 in this spot. So what I'd like to do is make that -4. I want to get a 0 in that spot. Well, to get it all, what can I do with equations? What can I do with equations such that I'm not changing the system of equations? If I have 3 equations, I can switch the order of the equations. Okay, that's what I did here. That was a row operation. Another row operation would be I could add 2 equations to each other, or I could multiply one equation by a number and add that new equation to another equation. Okay, you did that kind of thing with the addition-subtraction method back in Algebra 2. So the fact that I don't like the -4 here, it isn't that I don't like it, but I want to simplify my equations. I want a 0 where -4 is. So what I can do is I can multiply the first row by 4. Okay, that's what this instruction means. Take row 1, R1, row 1, multiply it by 4, and then add it to the third row. And then that whole result, 4 times the first equation plus the third equation, replace the third equation with that. Okay. So, what do we have here? Well, all right. So, and we're doing this in our mind. Okay. We could write out the steps, but there's already enough steps to worry about. So, if I multiply the first equation by 4, then in my mind, the first equation is going to be 4x1 minus 8x2 plus 4x3 equals 0. Okay, that's just by multiplying through the first equation, the first row. Remember, each row is an equation. The first row I multiply by 4. I don't really want an equals there, right? We're getting away. All right, so first row, first equation becomes 4x1 minus 8x2 plus 4x3 equals 0. Now the third equation, remember, is -4x1 plus 5x2 plus 9x3 equals 9. I'm going to add those equations. I'm going to add them. And when I do that, 4 and -4 gives me this 0 here. 4 plus -4 gives me 0. -8 plus 5 gives me this -3 here. And 4 and 9 give me 13. And then 0 and 9 here give me, hold on, I got one moment here. That's a -9, right? Should have there. 0 and -9 give me -9. So what I'm doing here in this thing that I've written down is I'm telling you what's going on in my mind. Okay, I mean, I can do this in my mind easily. But if I work with just the numbers, it's easy to do in my mind. The first row becomes 4, -8, 4, 0. I add that to the third row, and that's going to get me 0, 0, -3, 13, and -9. Okay, that's an elementary row operation. So 4 times the first row plus the third row, and I replace the third row with 4 times the first row plus the third row. Let me see here. Tizab has a question. Why don't we just add 4 at row 3 and replace -4 with 0? Well, you can't add. Adding numbers to equations is not a elementary row operation. Think about when you learned about the addition subtraction method, back when you were solving like systems of 2 equations with 2 variables. I mean, you never added, and all good questions are good ones. Do you ever recall adding a number to an equation? If you think back, do you ever recall that? See, you can't add, so Tiziab, you can't add, if, yeah, I want to, okay, hold on, Francesca, one moment. Remember, I think I can address your question here. Remember, to say, Gazib, I hope I'm saying that right, that there are variables understood to be here. These are not just numbers. They are coefficients of variables. Okay? You see what I mean? So does that make it a little clear why what you're thinking about would not work? Okay. Sega. Okay, very good, Sega. Francesca, how do you switch notation? So what? Okay, so when you have the symbol with the 2 arrows here, that means you're switching rows. But what this symbol here means with just the arrow means multiply the first equation by 4 in your mind, add it to the third equation, and then replace the third equation. I'm not saying this right. Replace the third equation with 4 times the first equation plus the third equation. That's what it means. All right, Francesca? Is that? Okay, great. Divihara asks, after you multiply the top row by 4 and add it to the third row, How is the top row still intact? Well, all I did was I used the first row. But okay, think of it like this. I got it. So what Divahar is saying is, well, gee, Dr. Judy, you multiplied the first row by 4. So the first equation is 4x1 minus 8x2 plus 4x3 equals 0. Okay, now in my mind, I'm going to multiply the first equation by a fourth. Okay, I can do that. I can multiply through by a fourth in my mind, and then the first equation is back to 1, -2, 1, and 0. You see, 1, -2, 1, 0, that equation is the same as 4, -8, 4, 0. So it's like I used the first equation to help me, but you know, it's still there. Okay, does that help a little bit? Does that? Okay, great, great. That's right, Divahar. That's right. Okay, okay. So now, what do we do next? What do we do next? Well, what we want to do is we want to hold on here. Okay, one moment. What we want to do is we like having zeros. So what I want to do is I want to get a 0 in this spot here, in the second column. You notice I'm kind of working downward. I'm working downward. So I want to get a 0 in this spot here. Okay. This is called the forward phase of our row operations, the forward phase. So the first column, are we happy with the first column? We should be happy with the first column, right? Because the first column has, you know, I mean, a 1 and 2 zeros. We're happy. The second column, it'd be nice to get a 0 where that -3 is. So what can we do? Well, we can work with the second and the third equation. So let me go over here. Hold on here. This isn't where I want to be. Yeah, this is what I want. So what I'm doing is I want to get a 0. Let me put this in blue. I want to get a 0 where the -3 is. So in my mind, okay, well, I can use the second row. I can use the second row here to help me. As a matter of fact, I'm going to do that. I'm going to use both the second and the third rows, which of course means the second and third equations. I'll multiply the second equation by 3, and I'll multiply the third equation by 2. Because if I do that, what I'm going to have is, I'm going to have, for the second equation, 0, 6, -24, and 24. Okay, so in my mind, that's what the second equation is now. And then the third equation, multiplying the third equation by 2, in my mind, what I have is 0, -6, 26, and -18. And then in my mind, right, I'm going to add those two equations. And then the result is going to be put in the third equation. I'm going to replace the third equation with this result here. And you can see that that's going to give you then the third row, a third row. And we got a 0 in the spot that we wanted. Diva is asking me, is it the goal to manipulate the equations to get as many zeros and ones as possible? Yes. Yes, that's the goal. So what we're trying to do, well, what we got this matrix in is what's called triangular form or echelon form. Okay, triangular form, or also known as echelon form. Okay, so let me just see here. One moment. One moment. So again, you know, in the ebook, they will mention these kind of things. And let me just see here. I'm checking one thing out here. Okay, so one moment here. Yeah, so you know, they again, you know, well, all right. So what's this echelon or triangular form mean? Well, notice in the matrix, the bottom, or the I should say, the bottom left corner, I have a triangle of zeros. That's called triangular form or echelon form. And we can solve the system now. We ought to be able to solve the system easily now that it's in that triangular echelon form. We have manipulated, Vivian, the system of equations enough so that I can figure out what one of the variables is. What's one of the variables is? What's one of the variables? So we're looking to solve for x1, x2, and x3. And Matthew's right, x3 equals 3, because the last equation reads 0x1 plus 0x2 plus 2x3 equals 6. And so therefore x3 is 3. So at this point, the system of equations is starting to unfold. We know what x3 is. And now, like one of the students commented, we could plug x3 back in to the first two equations here, and then solve for x1 and x2. But I would say to you, why stop there? Why stop there? Why don't we try to continue with some more row operations so that we can get our system of equations, get more zeros in there? Okay. So, but I'm not going to work downward anymore. I'm not going to do the forward face anymore. I have to start thinking about doing the backward face. Okay. So I want to go to we will continue, but what I mean is everybody good so far before we move on? Are we okay? This is what's called an echelon form. Okay. The column operations are just row operations. We call them row. We don't do column operations. We do row operations. Good question, Matthew. All right, so let's break this system of equations down a little more. Okay. Right, we did row switch, we did let's see here. Hold on. One moment. So the row operations, and I don't want to kind of digress to the book, but row operations, there are three ones that the book talks about in section 1.1. One is interchanging two rows. Another is replace one row by the sum of itself and a multiple of another row. But you could also replace, I mean, we did, we multiplied two rows in our mind and added the rows together and did a replacement. But basically, row replacement, row interchange are row operations. But now, what I'm doing now is that one, it was very helpful. So what I'm going to do is I want to rewrite the third equation here in a little bit easier way. Instead of 0026, what would be nice to have? Instead of 0026, it would be nice to have 00 blank blank. 00 almost right, Francesca. That's right, Robin. 0013. I can take the third equation, the third row, multiply it by 3, and then place the result back in row 3. So it's equivalent to saying, hey, if 2x3, 2 times x3 equals 6, then x3, 1x3, is equal to 3. And now I got a 1. And 1 is actually what's called, the book calls that a pivot. It calls that a pivot. Now the question is, what do you think we're going to do with that 1? Why do we want the 1 there? What are we going to do with it? Keep in mind we have these two, quote, complicated equations. The first and second equations are a little bit complicated. We want to make those first and second equations easier. We want to break them down a little bit. So how can this pivot here, the pivot 1, help me? Oh, Michael says multiply the third equation by 8. Okay, and then do what? Multiply by 8 and add the third row to the second row. Right? So in other words, if I go 8 times 1 and add it to -8, that's going to give me a 0 there. That's going to give me a 0. Let's try to make this maybe in green here. Yeah, Michael, you're on the right track. And then we're going to take the 1, and if I want to get a 0 in this spot here in the first row, I'm going to take my pivot 1 and multiply it by what? -1. That's right, Christy. Very good. So that's what we're going to do. And when I do that, the system of equations breaks down to this system of equations. So what I did was I took, and this is sometimes what's called the backward phase. We're doing, this is called the backward phase of the row operations. Because now we're producing zeros above the pivot, When we did the forward phase, we produced zeros below that pivot 1 in the first column. Now we're producing zeros above the pivot 1 in the third column. Yeah, I mean, I don't know if I'd call it back substitution because we're not substituting anything, but we are working, Michael, we are working backwards. In a sense, we're working, so 8 times the third equation plus the second equation, replace the second equation with 8 times the third equation plus the second equation, and then replace the first equation with -1 times the third equation plus the first equation. Are we okay now with these numbers that you see in the first two rows? Are you okay with how we got? I mean, really, all that got changed, right, is the 1 and the -8 became 0 and 0. Okay, are we okay so far? Let me know, please. Robin's good. Let me know if you have any questions. There's no bad questions here. Good. All right, so you're feeling good. You're feeling good. Hey, do you like the second equation? Is the second equation, you know, is there something we could do to maybe make that second equation a little bit nicer? Incidentally, do we know what x2 is based on the second equation? That's right, Michael. x2 is equal to 16. And you know, we can, of course, we can write the second equation as 0, 1, 0, 16. I can multiply through the second equation by 1/2. So replace the second equation with 1/2 times the second equation. Hey, what's this 1 called in the second equation? What do we call that 1 there? That's a pivot. Well, all right, pivots, we use pivots for things. What are we going to use that pivot for? Can we break the first equation down a little bit? Can any of the numbers in the first equation be replaced with a 0? Can any of the numbers in the first equation be replaced with a 0 using that red pivot there? That's right, Christy, the -2. And Divahar's right. Multiply the second equation by 2 and add it to the first equation. Wow, excellent, excellent. Okay. So let me see here. Hold on. To do that, we have to go to the I mean, that's going to be on the next page. May I move to the next page? Are we good? Kevin's good. Christy's good. Is it helpful? By the way, I'm trying to use. I'm circling things using the marker. Is that helping? Good. All right. Thank you. Wonderful. Wonderful. Good to hear. Good to hear. And we're trying to make this course as close as we can to a face-to-face class on campus. Okay, so I'm going to multiply the second row by 2 and add that 2 times row 1. I'm going to add it to the first row. Okay, sorry, 2 times row 2 and add it to the first row. If we do that, then this is the result. 1, 0, 0, and 29. That makes sense because, let's see, 2 times 0 plus 1 is 0. 2, wait, hold on. No, I don't want to do that. I just, mosquito was in my airspace. I had to take care of him. It's okay. I normally like to leave the bugs alone, but you know, so he's off to a better world hopefully here. So, but I love our world, right? So, okay. So, right. So, are we okay getting to this step here, where our system of equations is this? I just want to make sure you're good with it. And we took the 2 times the second row plus the first row. Replace the first row with 2 times the second row plus the first row. Let me double check my own notes here. Yeah. Okay, so Kevin says it's always going to work out so that there's only one pivot in each, you mean in each column? Yeah, pivots we think about that well, I got to be a little careful, but let's think about column. So if we have a pivot 1 in each column, and then we use that pivot to get zeros in the rest of those columns where the pivots are, then we've done the best we can. And at that point, the system of equations is in what's called reduced echelon form. Reduced echelon form. So that is going to be our goal, Kevin. That is going to be our goal. Now, reduced echelon form is actually, that term is from section 1.2. So this example really brings in ideas from section 1.1 and 1.2. But yeah, that's the best we can do. We can't break down the system anymore. And so this means then that, well, Divahart, you don't need to get it in reduced echelon form necessarily to find the solution. Once we got it in regular echelon form, we were able to figure out what x3 was, and then, but you know, the thing is, you almost actually to do it completely, you do have to get it in reduced echelon form, because even when we got it in echelon form and we knew that x3 was equal to 3, we still had work to do. So we might as well go all the way. I mean, this is the most efficient way. This is the most efficient way to solve the system, is to get it in reduced echelon form. And now the system of equations, the matrix, which is an augmented matrix, becomes, I write out the corresponding equations for the augmented matrix. And so now I know what x1 equals 29, x2 equals 16, and x3 equals 3. Okay, great, great. And so now the solution is 29, 16, 3. this point lies in all three planes. So these three equations, which represent three planes, intersect at a point. And the point is 29, 16, 3. Okay, give you a moment to copy that down. Okay, are there any questions on that? Okay. I want to go to the whiteboard to do another just little quick example, sort of one that I just sort of thought of in my mind, but does everybody have the example copied okay? Are we good? Okay, great. Wonderful, wonderful, thank you. Okay, lots of good participation here. All right, so I want to go to the whiteboard, and I'm going to ask a question here. Does the system, I'm going to write a system down here, x1 plus 2x2 this is just a little system. X1 plus 2x2 equals 0. And then x1 plus 2x2 x1 plus 2x2 equals 4. Okay, does that have a solution? Okay, Michael says no. Okay, well, what do these two equations represent geometrically? These two equations. I mean, if we think about an x1 axis and an x2 axis, Michael's right, they're lines. So Michael, you don't think that this system of equations has a solution. If the system of equations doesn't have a solution, then what does that mean geometrically about these two lines? They never intersect. That's right, Divahar, and Sega's right. They're parallel. These two lines would have to be parallel. Parallel lines don't intersect, so there's no solution. Now, how can you sort of spot this in terms of matrices? Well, okay, we can write down the augmented matrix. Okay. And I'm going to leave the first equation alone. But in this first equation, what's that one called? That first one there? That's a pivot. What am I going to use the pivot for, everybody? What do I want to use the pivot for? Multiply and replace. That's right. So, of course, my goal is to get a 0 in this spot here. So how would I do this? I'm going to take the first row, multiply it by a number, add it to the second row, what number am I going to multiply the first row by? -1. Good. So that's right, Divahar. -1 times the first row plus the second row, and the result gets put into the second row. That's exactly right. I'm not sure you wrote it quite right, Michael. I'd have to look at it again. But all right, so if we do that, what are we going to get? What are we going to get here in the second row? Right. Well, almost right, Divahar. We're going to get 0, 0, and maybe I'll put that in blue. That's right. Hold on. We're going to get 0, 0, and 4. 0, 0, and 4. Okay, so far so good? All right, so I'm looking then at that second equation, 0, 0, 4, and I'm saying, okay, second equation, which is 0, 0, 4, the second row is 0, 0, 4. That means the equation that goes with that is 0x1 plus 0x2 equals 4. Okay? So I'm not worried about the first equation. I'm worried about the second equation right now. Does 0x1 plus 0x2 equals 4 have a solution? Are there any x1 or x2? No, that's right. Max is right. So, I mean, 0x1 plus 0x2 equals 0, right? Does 0 equal 4? No, it doesn't. So that means no solution. No solution. Okay. So when you see in an augmented matrix, or when you do row operations, remember, it's an augmented matrix. I mean, we don't draw the dashes in, but you can. But remember, the augmented matrix represents a system of equations that is in, we're manipulating the equations, and we have it in reduced form. So when you have a 0, 0, if you have a row of zeros followed by a non-zero number in any row, that system's not going to have a solution. Okay? Does that make good sense? Good, good. Wonderful, wonderful. Well, all right. I'd like to move on to do perhaps maybe a few more examples here, because I'm thinking about your section 1.1 homework. I'm thinking about the type problems you're going to have. incidentally, if a system of equations does not have a solution, then that system is called inconsistent. No solution means inconsistent. And if a system inconsistent, if a system of equations has a solution, we call that system consistent. All right, are we ready to move to the next example? All right, great. Okay, so let's go ahead and do that. Let's go back to our share files here. And I want to move forward here. Okay, let's take a look at this example. So, you know, we get, this course is a little more abstract than other courses you've taken. There's a lot of conceptual thinking that goes on here. Okay, and this is a conceptual problem. So let me give you a moment to copy it down. Okay, so here we want to determine the value or values of H such that this matrix is the augmented matrix of a consistent linear system. Right, so, well, you know, in order to answer this question, you know, we need to understand the system better. How do we understand the system of equations better? You know, what is it going to reveal to us? We have to break the system of equations down by using row operations. So I have a pivot here, And I can use the pivot to produce a 0 in this spot here, okay, where the 3 is. So we should do that. That should be our goal right now in order to answer this question. Okay, so I'll move to the next page then, if we're good. Okay, so let's see here. Okay, so this was our augmented matrix that goes with the system. Well, they gave an augmented matrix, and I multiplied the first row or equation by -3 and added it to the second equation as I said as we knew we were going to do. And we replaced the second equation with -3 times the first equation plus the second equation. And this is what we get in our second row. So let's make sure everybody's comfortable with that. The 6 minus 3h is there because, you know, -3 times h plus 6 is 6 minus 3h. Okay. So are we okay with up to this step? Are we good? Are there any questions? All right, great. So what do we do now? What do we do now? Well, you know, we're trying to find some constraint on H such that, you know, we would have a consistent system. So I certainly, I mean, I can certainly, to make it a little more concrete, I can go ahead and write out the second equation. I mean, I do have the two equations, both with H in them, but let me write out the second equation. Second equation reads 0x1 plus the quantity 6 minus 3h times x2 equals -4. And that means then that 6 minus 3h, the quantity 6 minus 3h times x2 equals -4. So again, you know, they're asking what values of h. Well, you know, there's an infinite number of values of h that we have to worry about, right? H is a variable, it could be any value, but what value would make it consistent? And the only answer here is that the system is consistent only when h is not equal to -2. Now, why is that? Why is that? Well, first of all, you know, I'm interested in what 6 minus 3h, that coefficient, equals. And so I say to myself, well, you know, 0 is an interesting number. So what value of h would make 6 minus 3h equal to 0? Well, that would be h equals 2. Why is that important to me? Why is that important to me? Well, if h equals 2, then the second equation would, you know, let's just try. Let's put in h equals 2. If h equals 2, the second equation here is going to become 6 minus 3 times 2 times x2 equals negative 4, or 0 times x2 equals negative 4, and that has no solution. So when h equals 2, the system has no solution. Let me let you copy that down for a moment. Hold on. Okay, so when h equals 2, we know the system will be inconsistent because plugging in a value of h equals 2 will give us that 0x2 equals negative 4, and there's no solution. But why is that? It's because we have a 0 coefficient in front of x2. Now, if h is not equal to 2, then we're going to have a non-zero coefficient in front of x2, right? We would have a non-zero coefficient in front of x2. And that would mean that we can solve for x2. Okay, so like, what's a non-zero coefficient? What if h were equal to 1? If h were equal to 1, you'd have 6 minus 3 times h. That means you'd have 3x2 equals negative 4. We can solve for x2, right? x2 is equal to negative 4/3, and then we can back substitute and solve for x1. So h equals 1 works. Okay, if h equals 5, 6 minus 3h, that would be 6 minus 15, that would be negative 9. x2 equals negative 4. Again, we can solve for x2. We can solve for it, and then we can back substitute and solve for x1. So this is why the system is consistent only when h is not equal to 2. Okay, does that make sense? Are there any questions on that? All right. Thank you, Kevin. Thank you, Vivian. Okay, thank you, Michael, Christy, Francesca, Joseph. So I'm trying to learn names. Michael. Wonderful, wonderful. Well, let's do another example then. If we're good with this one, let's do another example. Okay. Okay. Let's determine the values of h such that the matrix here is the augmented matrix of a consistent linear system. Notice here that the h is in the second row. It's just an observation. Okay, so we want to determine the values, okay, of H, and maybe they're none, okay? Or maybe, I mean, you know, I want to be careful. You have to be kind of ready for anything, right, in these kind of problems. Um, so again, they nicely put 1 there as my pivot, and we'll use the pivot to eliminate the -4. Well, we'll make it to make it a 0. So we'll multiply 4 times the first row and add it to the second row. And then that equation will replace the second row. Okay, so, and this is what we have. All right, are there any questions? Any questions on this matrix here, where we're at? Yes, Divahar, yes. So say the third term of the second equation was not 0. Okay, okay. So no, not necessarily. No, it would, I think, be a harder problem to work with. I don't want to digress too much, but I understand what you're saying. You're kind of playing around with the possibilities. I mean, some of the possibilities. I mean, I think, you know, we'll focus on this, but we can chat about something like that at maybe at office hours, if that's okay. I mean, I want to answer it, you understand, but I don't want to get too. It's an excellent question, but you know, okay, very good, very good. So okay, well, how are we going to answer this question? Again, I always in math like to take things and make them a little familiar. So I know this is an augmented matrix, and I can certainly write down the second equation. I can write that equation down. And it turns out, well, you know, we want to know what values of H that second equation is going to be going to hold for. Would it work for instance, H equals -12? It would, Michael. That's right. Because if H equals -12, and again, you know, you know, I just work it right out. I mean, I like things to be crystal clear. I'm going to put in H equals -12 and see. Okay, well, 12 and -12 make 0. 0 times x2 is 0. Oh, so x2 0. Let's see. Hold on, Michael. Hold on. I want to say Michael's name's right. Mikkel. Mikkel. Okay, great, great. Thank you, thank you. Yeah, so, you know, if h equals negative 12, the second equation becomes 0x2 equals 0, so x2 equals 0. Okay, well, that's good. That's good. You know, we won't have an issue there. And you know, you could, incidentally, I should mention the first equation, right? If x2 equals 0, then what we're going to get is x1 equals negative x2. So, I mean, you do have to really look at both equations to make sure. But clearly, there's the first equation is not going to offer us any problems. Okay, it's the second equation where we could run into a problem. Now, the second equation also, what if h were not equal to negative 12? What if h were not equal to negative 12? Well, then that means that, well, I mean, we have that x2, you know, we have 0x1 here, but that's gone then, right? So we can solve for x2. x2 equals 0 divided by 12 plus h, you know, based on what we have here. And 12 plus h would not equal 0 if h is not equal to 12. And so it would be like taking 0 and dividing by a non-zero number, and that gets you 0. Okay. So whether h is negative 12 or not equals negative 12, it works for all h. The system is consistent for all h. Okay, does that make good sense? Good. Excellent, excellent. And you know, sometimes, like, what might happen, like in my math lab, and we're actually going to go to my math lab. I want you to work a little bit on your exercises that are due Thursday. I always like to allow a little class time. We may not be able to allow all the class time, but we can allow some. But you know, sometimes what happens, I mean, my math lab, basically every problem, I want to be careful how I say it. Some of the problems, there's like a help me solve this feature available. And sometimes, I mean, I guess what I'm trying to say is the help aids are good. But, you know, sometimes in the help aids, like they might stop here. Okay, they might say, so the system is consistent for all h. Or they might stop here and say, you know, so the system is consistent for all h. I mean, I would hope they would offer a little more, but what I'm trying to say is you have the power in yourself to if you're having trouble and the help aid isn't giving you enough information, you can always do a little more on your own to help you feel good about your answer. What am I trying to say here? You know, that's part of just getting a little more comfortable with math. I want to just everybody's good with this example. I'll move. I want to make a comment on that previous example, but everybody has this copied down okay? Wonderful, wonderful. So, you know, if it ever is the case that you don't, email me right away and say no, you know, and then, but okay, the previous problem, I just want to look at one thing here. So, yeah, you know, the first equation, so, you know, the way I did it, you know, we had looked at the second equation, but really you do have to look at both equations. And the first equation is not going to cause us any problem, no matter what h is. Okay, so you know, this first equation here. So All right, I feel a little better now. All right, well, what I want to do is I want to stop the recording.